Okay, let's begin. Now for any series, you're going to start off with the divergence test. Essentially, it is the quickest, the easiest, and also the most straightforward test. Essentially, you take the limit of the function as it approaches infinity, of the series, and you're going to see if it does not equal 0. If it does not equal 0, if it equals infinity, if it equals 1, any number other than 0, you know that the series diverges. However, if it equals 0, then it is inconclusive. Now, once you do the divergence test and you come up with an inconclusive answer, you're going to ask yourself a series of 3 questions. Now, first question, is the series alternating? What I mean by that is it of the form -1 to the power of n, -1 to the power of n minus 1, or any other variation of that? Or is it an oscillating trig function? So sine of n, cosine of n. If it is an alternating series, it will be very, very obvious. That's the first thing that usually catches your eye. And if so, you're going to use the alternating series test. To refresh your memory, this is a test where you basically take the absolute value of the series and you look to see if it is decreasing and if the limit of that series equals 0. If so, you have proven convergence of the original series. However, from there, if the question asks for absolute or conditional convergence, what you do is you take you test the absolute value of the series. This time you're actually testing the absolute value of the series for convergence or divergence. And if it converges, then you have proven absolute convergence. If it diverges, then you have proven conditional convergence. And so the alternating series test usually proves conditional convergence, but you cannot use the alternating series test to directly prove absolute convergence or divergence. So that's out of the picture. Now, say that the series is not alternating whatsoever. Then you're going to ask yourself, is it of the form, an exponential form, some type of exponential form? Within an exponential form, there are 3 possibilities. The first possibility is n to the power of p. If you have the form n to the power of some number, then you're going to be using the p-series test. If p is greater than 1, it converges. If p is less than or equal to 1, it diverges. So p-series test can be used to prove convergence or divergence. Now, if it is of the form n to the power of n, you're going to be using the root test. Remember that the root test can be used to prove either convergence or divergence, or it can be inconclusive. So the last exponential form is r to the power of n. If you have some number r to the power of n, then you're going to be using the geometric series test. This is also another straightforward and easy test to use. If r is less than 1, then it converges. If r is greater than or equal to 1, then it diverges. So geometric series tests can be used to prove both convergence or divergence. Now let's go back to the top here. First, we asked ourselves, is it an alternating series? Next, we asked ourselves, is it an exponential form? The third thing you want to ask yourself if the divergence test fails is, does it have a factorable denominator? So basically, is the denominator a polynomial form that can be factored very easily? If it does have a factorable denominator, you're going to be using the telescopic series test or the nth partial sum test. This is a test where you basically find S of n, or the sum of all of the terms, and you basically test to see if the terms collapse, basically if they cancel out within each other. If so, it converges. If not, it diverges. So the telescopic series test can be used to prove both convergence or divergence. Okay, so we've already gone through 6 of the tests. Now let's zoom out a little bit. Say that you've asked yourself all 3 of these questions. Is it alternating? Is it an exponential form? Does it have a factorable denominator? And say that your answer is no to all of them. What you're going to do then is you're going to ask yourself another set of 3 questions. Also note that if you took the root test and it comes out as inconclusive, then you can also go down this path. So the first question you want to ask yourself is, does it resemble a p-series or a geometric series, but it doesn't quite look very right? One example of this would be something like 1 over n squared minus n. You have the n squared or the n to the power of p, but there's another component attached to it that makes your life just a little bit harder. If so, then you're going to go down to the direct comparison test. Now for direct comparison test, what you're doing is you're taking the original series, you're making a new series that is a lot easier to test, and then you're comparing it. Is it greater than or less than? Now remember that for direct comparison tests, there are only 2 combinations that work. That is, if b of n is greater than a of n, and b of n converges, because remember, if a bigger series converges, then a smaller series must converge. Or if b of n is less than a of n and it diverges, because remember, if a smaller series diverges, a bigger series must diverge. So those are 2 combinations that work for direct comparison test. Now, however, if you somehow can't get either of these combinations, so let's say that you've chosen a b of n that's greater than a of n, however, it diverges. So there's like a mixed match between these 2 combinations. So if the combinations don't work, you're going to use the limit comparison test. Now, the limit comparison test is pretty similar to the direct comparison test in that you have original series a of n and you choose another series b of n to compare it to. However, you're going to be taking the limit as like n approaches infinity of a of n over b of n. And if that is greater than 0, then a of n basically does whatever b of n does. So this shows convergence or divergence. Now, in most cases, the limit comparison test can be used for more functions than the direct comparison test, because direct comparison test, the conditions are a lot stricter than the limit comparison test. And so personally, I like doing limit comparison tests more. It's easier, but direct comparison test is also very effective. But remember that if direct comparison test fails, you should use limit comparison. Now, let's go back to the top. Let's say that the function does not resemble a p-series or a geometric series. Now you want to ask yourself, is it easy to integrate the series? So is the series just screaming out for you to integrate it? Examples of this would be easy U substitutions, or just an easy integration technique that you can apply to the function. If so, then you're going to use the integral test. Remember that integral test, it must pass 3 conditions. The series must be continuous, it must be positive, and it must be decreasing. It must pass all 3 of these conditions in order for you to use it. Basically here, you're taking the integral from whatever number it starts with to infinity and of the series. And you're asking if it diverges or converges, and whatever happens, that's what the series does. So this shows you convergence or divergence. Personally, I never want to use the integral test. I always try to look for another test I can use, but sometimes integral tests can be easy. but you don't want to use integral tests for any series that is impossible to integrate or it takes a long time to integrate, because you want to save time when you're doing these tests. I also want to note that if the limit comparison test fails, so the limit, so this condition happens to be less than 0, then less than or equal to 0, then you can also use integral tests. So if the limit comparison test fails, that's quite an obvious sign that you're going to be using integral test. Okay, so let's go back to the top. If it does not resemble a p-series or a geometric series, it doesn't look easy to integrate, then there's another question that you can ask yourself. Is it a complicated ratio? So it's a ratio, but it has like factorials or, exponents. So like x to the power of n, a number to the power of n, 3 to the power of n, pi to the power of n, something like that. And like a factorial, so like n factorial, a complicated ratio of some sort. That is a clear indication that you're going to use the ratio test. Now, ratio test, similar to root test, it can tell you both convergence or divergence, or it can be inconclusive. Now, if you do happen to get an inconclusive answer, and your series contains a factorial, that is a little bit complicated, right? You don't want to be using integral tests because you just don't want to take the integral of a factorial. Usually the case is if ratio test fails for a series with a factorial, you want to go back to divergence tests and see if you can manipulate the function in some way, or again take the limit of it and see if you took the limit wrong or something. But usually, if there's a factorial, you should be able to manipulate it in such a way that it resembles more of a geometric series, or you can take the limit of it. Okay, so that is it. Those are the 10 tests. However, I do want to say that if everything fails, so you've tried everything in your power and nothing seems to quite work, first of all, check your work, because there is a chance that you made a silly mistake along the way. Like, these tests are confusing sometimes, and so you want to be very mindful and very cautious. And then usually I would check the limit again. I feel like a lot of times I mess up, but then I take the divergence test again and realize that it was a quick divergence test and I took the limit wrong. And so, yeah, those are some advice I have for if everything fails.